Assalamualaikum and hello everyone. We would like to continue Mechanics of Materials, the last chapter, which is chapter 9, Buckling of Columns. Previously, you already learned how to analyze the elements, how to analyze the material, as well as how to analyze a beam. In this chapter, we would like to analyze a column. Column is the main structure of the building. For example, this is a building. From the roof, the load will transfer to the column, the slab will be transferred, the load from slab will be transferred to the column. A column will carry all the loads from the slab, beam and also a roof, and then it will transfer to the foundation. So here we can see that column is the main structure that sustains the load. So how it acts when the load is applied to the column. We would like to see how the behavior of the column when the load is applied. Let's take a look at the linear outcome. By the end of this chapter, you should be able to describe the concept of columns in terms of types of column, cross-sectional of shapes, industrial standard application, and slenderness ratio of a column. Illustrate, explain, and differentiate the failure mode of columns due to a buckling. Explain the influence of support conditions, the relationship between the effective length and radius of gyration, describe the compression member of long slender column, and apply the Euler formula to determine the critical load for a long column. Here you can see that the buckling, the failure mode of a column is a buckling. So it is a straight column, but when we apply some load here, then there will be a buckling. The buckling when your column is buckled. There is a slightly different of analysis when you have a different support condition, and then we would like to calculate the effective length. The effective length, from here we would like to know the Euler formula. Euler formula, here you can determine the critical load of the column. What is column? A column is a relatively long, slender member loaded in a compression. The structure element that transmit through compression the weight of the structure above to the structural element below. Columns are frequently used to support beams or arch on which the upper parts of walls of ceiling rest. For the purpose of wind or earthquake engineering, columns may be designed to resist lateral forces. Here is explained that column is long and slender, means that it's very long. For example, this is your column, and it is transmit to compression. Why it is compression? Because you have a load from roof or slab or the beam from upper part, and then it should have a balanced load from the foundation. So that's why it said that the column is in a compression, because you have a load from upper part and you have the load from down. Besides from vertical load, you also have a lateral forces. Lateral forces is usually from wind. So column should be able to sustain a vertical load as well as a lateral load here. This is an example of the columns design. You have a round column as well as you have a rectangular column. Depend on the design and also depends on the application of the column and how much the column can sustain the load. This is the structure taxonomy. If you look at here, this is your column, this is your beam, and inside here you will have a slab. So all the load from here will transfer to the column, here transfer to this column as well as transfer to this column. The slab also been transferred to this column, and all the load had been transferred to the column will be transferred to the foundation. And at the foundation also you need the equilibrium for column and also a foundation. Inside here you will have a soil bearing pressure. That's why I mentioned column here is a main structure of your building. When a perfect column is subjected to a compressive adhesive force as shown in the figure, the only deformation that takes place is a shortening of the column. For low value of F, if the column were to be deflected laterally by a force perpendicular to the column, and the lateral force were thereafter removed, the column will return to its straight position even with the force F remain in the place. This indicates a condition of stability. It means here, when you apply the force, if the force is still in the range of the allowable force, then when you apply the force, after you release the force, it will get back to its straight position. So the column should be straight. If your column is not straight, then we call it as a failure of a column. If your force here is still in the range of the allowable force, then your column is said to be stable if it can return back to its straight position. But if the load F will increase, there is a value of F for which when the lateral load is removed, the column will remain in the deformed shape. This condition is referred to as buckling, and the column is said to have failed from a structural standpoint. Buckling can also be described in the simple terms as bending or bowing of a column due to a compressive load. If you increase the value of force here and the column not be able to sustain this force due to the excessive force had been applied to this column, then your column will said to be buckled. If the column is buckled, then we said that this column is fail. Because when you release this force, it will still bend. Bend here is a buckling, is not straight, so the column is fail. So there are two types of column, which is a slender column, where the slenderness ratio is more than 20, so it will fail by buckling, means it will buckle like this. For short column, it will fail by shear if the slenderness ratio is less than 20. Fail by shear is like this, it is 45-degree failure. And some of the column will fail due to a compression. It will buckle in right and left side of the column. This is an example of the buckling, compression and shear failure of the column. So if you look at here, this is a compression failure. If it is 45 degree, we said that the column is failed due to a shear. If it is bolted at left and right side of the column, we call it as a failure due to a compression. And if you apply the excessive load here for a long slender columns, you will have failure due to a buckling. Cross-sectional shape for columns. A column is slender when it has a small cross-section compared to its effective length. Small is placed in the quotes due to the fact that the important information about the cross-section is both the actual size and, more importantly, the shape of the cross-section. This is done compared to the effective length to determine whether or not the column is slender. If it is, this means that the column will probably fail in bending. As a column is loaded, it is likely to bend about the weak axis of the cross-section with the lowest moment of inertia. A column buckles when it bends about an axis. This is a stability failure. When your column is buckled or bending, so the column is fail. As an engineer, there is a responsibility for you to design a column that can sustain all the loads. Because all the loads will transfer to the column, if the column is failed, then all the structure in the building will fail. This is an example of a column. You have a tapered column tapered here means that the up here and the down here column will have a different cross-section area. And also you have a rectangular column. You have a circle. This is a rectangular. For steel column, you will have a I shape. H, C, and depends on the application and also how much the load can sustain. The asterisk standard applied to columns, you can read you have three types of standard columns: a vertical column of steel frame building, a steel column holding up the building across the length of the basement of a hull, a slender rod of a hydraulic actuator. Slenderness ratio is a measure of how long the column is compared to its cross-section effective width. The slenderness ratio is the column's effective length divided by the radius of a gyration. So you have this formula: S is equal to L over R, where S is a slenderness ratio. L here is actually the effective length. Symbol of effective length is LE. This is the effective length. R here is a radius of gyration, and R here is equal to I over A. So I here is a moment of inertia, A is a area. From slenderness ratio, you will know that your column will fail at x-axis or y-axis. This is an example. You have x and y-axis. This is y, this is x-axis. So when you calculate the slenderness ratio, you will know your column will buckle at x or at y-axis. So if you look at here, this is a very long column, and this is a very short column, but the cross-section area is different, and you calculate for slenderness ratio, these two columns will have a same slenderness ratio. Failure mode of column. As I mentioned, a slender column will fail due to a buckling. When a slender member is subjected to an axial compressive load, it may fail by a condition called buckling. Buckling is not a failure of the material itself, as it is yield and fracture, but it is due to a geometric instability of the system. Note that buckling is not dependent on the material strength. It will depend on how much you apply the load to the column. So this is an example or illustration of buckling. When you apply a load here, then it will buckle. PCR is a critical load. P is a allowable load. If you apply a P more than critical load, then it will buckle. This one P here is a allowable load. P here is a critical load. If the allowable load is more than critical load, then your column will buckle. Which axis the column is buckled? Here, as I mentioned before, you have x and y axis. So if you look at here, can you see the buckling? Or if you look at here, can you see the buckling? You need to determine which axis the column is buckled. The other way to know which axis the column is buckled is by calculate the slenderness ratio. The column will buckle at the bigger value of slenderness ratio. This is a comparison of shapes for buckle column with a different connection. If you look at here, this is fixed connection. Then your column will buckle right here at the connection point. It will go straight, and then in the middle it will buckle. So this is for fixed connection. And here is a pin. Here is a fixed. At pin connection, it will start buckle at the pin joint, and then as this goes near to the fixed, it will go straight here. And here is a free because it goes straight, and then near to the free, it goes up here. This one is pin connection. At the starting point of the pin connection, it will buckle like this. Okay, this one also free fix, this one also free pin. So the most common connection that we will analyze is fixed fix connection, pin fix connection, free fix connection, and pin connection. If you look at the buckling shape, you will also have a K, the factor, to calculate the effective length. So influence of support condition to the effective length. So for pin connection, we simplify the drawing. This is a pin connection. If we start at the pin connection, and it will goes here. So this is your effective length, where your LE is equal to L. And if you have a fixed free connection like this one, fixed like this, and free here, this one, your column will buckle in the mirror image. So here your LE is equal to 2L, the original L here for your column. And LE is actually a buckling shape of that column. The third one is a fixed connection. So for example, this is your column with fixed connection. Here your column will buckle at fixed connection, it goes straight first, and then it will buckle in the middle, and as it go near to the fixed connection at the bottom, it will go straight. So your LE is equal to 0.5 L. This is your original L. Then you times 0.5, you will get your effective length. The last one is a pin fix end. Up here is a pin, or up here is a fix. As long as it pin fix, it will give you the same effective length. That pin here, it will buckle, then as it goes near to the fix, it will go straight. So this one is your LE. So LE is equal to 0.7 L. So this is the effective line factor that you need to know. For pin ends, the LE, the factor is equal to 1. If it is fixed end, your LE is equal to 2L. Fixed connection, then you have LE is equal to 0.5 L. And for pin fix, you have LE is equal to 0.7 L. Means that to calculate the LE, you need to times K, which is the factor, times the original line. What is effective line? How a column is supported governs its buckling strength. The effective line LE accounts for differences in the end support. The effective line is the length the column would be if it were buckled as a pin column. A dimensionless coefficient, K effective factor, is used to calculate LE. As I mentioned before, you have 4 types of column connection. Then effective line is where it is buckled. So you need to time the effective line with a K factor. So this is the same explanation. You can go through to the lecture note later. Radius of a gyration. If all of the cross-section area A will mass a distance R away from the bending axis, the idealized lump area cross-section will have the same amount of moment of inertia I as the actual cross-section if R is equal to AR square. Distance R is the radius of a gyration there are generally two bending axes to consider, which is x and y axis, and thus the two gyration, which is the general equation for radius of a gyration is r is equal to I over a square root. But if it is a rectangular columns, then you will have different moment of inertia. Okay, moment of inertia for IXS is different with moment of inertia of IYY. You need to calculate two times, okay, for RX and RY. Then after that you can calculate for SXX and SYY. From S value here, you will know that the column will buckle in which axis. The magnitude of the load at which buckle would occur. Columns are long slender members subjected to an axial compressive force. Lateral deflection on a column is called a buckling. The maximum axial load that a column can support when it is on the verge of buckling is called a critical load, which is PCR. Factor of safety is a safety margin given in design so that the member will not fail when the load is increased beyond the elastic limit or when the size is reduced. Normally, the factor of safety is varies between 1.4 to 3 for column design. Usually, we will not go up to 3 factor of safety. We limit it between 1.4 to 3 factor of safety. So factor of safety here is equal to P ultimate divided by P allowable or PCR divided by P maximum. Same goes if it is stress. P is a load, sigma is a stress. Because you know that sigma is equal to P over A. Remember back the first chapter. This one, or critical stress divided by maximum stress. The important theory is the Bernoulli theory, which is we will get the Euler formula. Euler formula used to calculate the critical load of the column. So how to derive the critical load is by assume that both ends are pinned so they can freely rotate and cannot resist a moment. The critical load PCR required to buckle the pin column is given to you by this equation, which is PCR is equal to pi square EI divided by LE square. L here is actually LE square. So E is modulus of elasticity, I is equal to moment of inertia, LE is effective length. Here, if you have X and Y axis, if it is rectangular, then you have PCR XX and PCR YY. Okay, it depends on the equation. This is the derivation of the Euler formula. You can read the derivation, you need to integrate and you need to differentiate the formula with the Bernoulli equation and also the load equation. Then the last thing you will get this one, which is critical load is equal to pi square EI over LE square. The assumption of Euler formula is the column should be axially loaded column. It should be a perfect straight, isotropic and homogeneous material, means that the material along the column is same material, is made from same material, and the material behave within elastic properties, and both ends of a column support are being supported. If the column is not being supported, then you need to include the K factor here. Okay, this is actually the K factor, which is the effective length. So that's why in this formula I put it as a LE, so that you just remember one formula and then you just calculate with LE. If you calculate with L, then you need to put the K factor in front. but if you use LE, then you just put the LE value. Let's take a look at the first example, example 9.1, redication. A 3.6 meter wooden rectangular column has the dimension shown. Determine the critical load if the ends are assumed to be pin connection. The E is equal to 12 gigapascal. Mentioned here, it is a pin connected at both ends. So, this is your column. It is pin connection. For pin connection, the buckling start from pin to pin. So first thing you need to do is to calculate your LE. LE is equal to L. So therefore, LE is equal to 3.6 meter. First step is for draw buckling shape and effective length. After you get the buckling shape and the effective length, the question asks you to calculate the critical load. You know that PCR is equal to pi square ER over LE square. If you look at here, this is a rectangular column. This is your x-axis, this is your y-axis. After you calculate your effective length, then you need to determine which axis your column will buckle. So we start with slenderness ratio. To calculate the slenderness ratio is equal to LE over R. Then R here is equal to R over A square root. So since it is a rectangular column, then you need IXX and IYY to calculate RXX and RYY. Therefore, you can calculate the slenderness ratio for x-axis and slenderness ratio for y-axis. Then you can determine which axis your column will buckle. And after you determine which axis your column will buckle, then you can calculate the PCR, which is a critical load. So let's start with RXX and IYY. And this is the diagram if you would like to calculate for IXX. Is equal to BH cube over 12 is equal to, I would like to use in meter. For IYY, you just rotate the diagram. Now it becomes, here is Y, here is X with the same dimension. This is 50 mm and here is 100 mm. For IYY, after you calculate your I, then you can calculate your R. RXX is equal to IXX divided by area square root. RYY is equal to IYY divided by area square root. Area is 6, okay, because area is B times D. After you get your RXX and RYY value, then you can calculate for slenderness ratio. Therefore, based on slenderness ratio value, then column will buckle at Y axis. Because if you look at the slenderness value, S value is bigger than X value. So the column will buckle at Y axis. From here, then you can calculate the PCR value. Now is PCR for Y because the column will buckle at Y axis. So PCR Y is equal to pi square E is given 12 times 10 power of 9 I. Now we will take a Y I Y Y. Effective length is 3.6 power of 2. Then your PCR is equal to, this is your final answer. If you would like to do for Y axis, then you can do. Get here, if your slenderness ratio is smaller, then your PCR is not. Your PCR is smaller. Let's take a look at the second example. The uniform column AB of 2.5 meter structural tubing having a cross section as shown in the figure below. Point A and B is fixed and free supported respectively. Using the formula and factor of safety of 2, determine the allowable axial load for the column and the corresponding normal stress. Take E is equal to 200 gigapascal. Here is a hollow. Inside here you have nothing. This is a hollow column. The area is given and the I is given here. This is power of 6 and the R value is given. Since the I and R value is given, then no need to recalculate the value. The question asks you to calculate the allowable load as well as the corresponding number stress is equal to critical stress. The question gave you factor of safety is equal to 2 and E is equal to 200 gigapascal. So first you know that FOS, factor of safety, is equal to PCR divided by P allowable. So here is what you would like to determine, and you know that the PCR is equal to pi square EI over LE square. And then it is also mentioned in the question that this is a fixed free connection. Then you draw. First is draw a buckling shape and effective length. So your column will buckle 2 times. So LE is equal to 2L. Then 2 times the original length, which is 2.5 meter. Then this is equal to 5 meter. After you get the buckling, then we would like to calculate for PCR. PCR is equal to pi square EI over LE square. Here I will use all in meter. If you would like to use millimeter, then you use millimeter, but make sure you know how to convert gigapascal in millimeter. Here I convert it using meter. For P we use kilonewton. From factor of safety, manipulate the equation, then you will get the allowable is equal to this is your answer for the allowable. And then the question asks you to calculate the corresponding normal stress, critical stress or Euler stress. Divided by area is given. I convert it into meter. Then you will get your answer for critical stress. So basically you need to know the effective line. Effective line is very important. So you need to remember the K factor. If it is fixed connection, then your LE effective line is equal to 0.5 L. If it is pin fixed connection, then your LE is equal to 0.7L. If it is pin-pin connection, then your LE is equal to L. If it is fixed-free connection, then your LE is equal to 2L. If the column is square column, then you will have the same IXX and IYY. If you have a rectangular column, then you will have a different IXX and also IYY. From that, you can calculate the radius of gyration. After you calculate the radius of gyration, then you calculate for slenderness ratio. Then you pick the biggest slenderness ratio. Please try this example. Example 3. The hollow steel column has a length of 4.55 meter and the thickness of 5 millimeter as shown in figure. If its ends are assumed to be fixed supported and it is subjected to the axle load of 500 kN, determine a slenderness ratio, Euler buckling load, factor of safety with respect to a buckling. Fixed connection. And then you need to draw the buckling shape. LE is equal to 0.5, L is equal to 0.5 times 4.55. Then your LE is equal to 2.275 meter. If you look at the question, mentioned here the thickness is 5 millimeter. So here is 5 millimeter. Here is 5 millimeter. Same goes to here and here. So when you would like to calculate your I or your area, you need to the outer minus inner dimension. After that, you calculate your RXX and RYY. And from here, you calculate your slenderness ratio. Then make the conclusion. Column will buckle at what axis? So you're done with question A. Question B is a Euler buckling load, which is a PCR. You calculate for PCRY and PCRX. For here, you will get PCRY please do the calculation, and for X you will get and C. You calculate factor of safety. They give you the allowable load is equal to 500 kN. Here we get from question B. The allowable is given, which is the applied load 500 kN. Then you will get your factor of safety. In y-axis is equal to 0.43. Factor of safety for x-axis is equal to 1.32. So this is your answer. Okay, for here you calculate. Please do the rest of the calculation. And please do this exercise. And it is partially restrained. Partially restrained means it is a in-fixed connection. So here, what is your inner diameter? After you get your inner diameter, then you can calculate the thickness. Please try this one. This is an example of final exam questions. They ask you to sketch a buckling shape, calculate the slenderness ratio, determine the maximum load with the given factor of safety, and then determine the ratio of axial stress corresponding to buckling load. So how to calculate the ratio? Ratio is equal to the buckling load, which is the buckling stress divided by the yield stress here. Then you will get your answer here. Please try this one. The area is given. ISX and IYY also is given. In here, if you look at the column that we analyze is a column without brace. We have another type of column which is brace column. Here is an unbraced column. In the second part of chapter 9, we will discuss how to analyze a brace column. Thank you.